On March 6, 1944, at an altitude of 28,000 feet over the German capital of Berlin, the 56th Fighter Group plunged into what would become the most extensive aerial engagement Europe had ever witnessed. Amidst the swirling dogfights, American Thunderbolt pilots unveiled a startling new capability that left their Luftwaffe adversaries utterly bewildered. For the past year, German fighters had relied on a nearly infallible escape maneuver, a rapid, steep climb that the heavy P-47 Thunderbolt simply couldn't match. Focke-Wulf 190s and Messerschmitt 109s would routinely pull away from pursuit, leaving American pilots frustrated and vulnerable. But on this pivotal March day, everything had changed. American fighters clung to the tails of their German counterparts through a sense that, by all previous standards, should have been impossible. As both aircraft neared their stall speeds at altitudes approaching 28,000 feet, Thunderbolt pilots unleashed their firepower. Black plumes of smoke erupted from the crippled German fighters as their pilots scrambled to bail out. By the mission's conclusion, the 56th Fighter Group reported 11 German aircraft destroyed, suffering no losses themselves. The transformation was complete. A seemingly minor alteration to the Thunderbolt's propeller had eradicated its most significant vulnerability, fundamentally shifting the balance of air power over Europe. The story of this critical technological leap began in the engineering offices of two American propeller manufacturers during the harsh winter of 1943, and its full impact, far beyond simple climbing, would soon become clear. While Allied bombers endured heavy losses over Germany and fighter pilots repeatedly reported German aircraft escaping through rapid climbs, engineers back home raced against time to resolve a deceptively straightforward issue. The Pratt & Whitney R-2800 engine boasted an impressive 2,000 horsepower, yet the P-47 Thunderbolt consistently struggled with vertical performance. The narrow-bladed Curtiss electric propeller, installed on earlier production models, simply couldn't convert that immense power into effective upward thrust. These blades were primarily designed for efficient high-speed cruising, optimized to minimize drag above 350 miles per hour. However, during climbs at lower air speeds with the engine at full throttle, these slender blades failed to sufficiently bite into the air, hindering the efficient conversion of horsepower into thrust. Engines roared at maximum RPM, consuming fuel and generating heat, but the aircraft lacked the necessary force to ascend effectively. In January 1943, at Republic Aviation Corporation headquarters in Farmingdale, Long Island, Alexander Kartveli reviewed incoming combat reports from England with increasing alarm. German fighters would dive through bomber formations, launch their attacks, and then execute steep climbs to evade pursuing Thunderbolts. The performance data was unequivocal and damning. Early P-47 models required extended periods to reach combat altitudes, a stark contrast to the Focke-Wulf 190A and Messerschmitt 109G, which ascended much faster. This disparity in performance directly translated to American casualties. Pilots perished in scenarios where superior climbing ability might have saved them. Some Army Air Force commanders even questioned the P-47's continued suitability for frontline service. Kartveli, an astute engineer, understood the core problem: propeller efficiency hinges on matching blade area to specific operating conditions. While narrow-bladed propellers excelled at high speeds by minimizing drag, during low-speed climbs, blades needed a larger surface area to effectively grip the air and convert engine power into thrust. Increasing blade area appeared to be an obvious solution, yet its practical implementation proved intricate. Every modification to propeller design had ramifications across the entire aircraft system. Incorrect blade shapes could induce vibrations severe enough to dislodge engines from their mounts. Improper weight distribution risked generating harmonics that could lead to catastrophic structural failure. Furthermore, unsuitable torque characteristics could render the aircraft uncontrollable during takeoff. Republic Aviation urgently required propellers with significantly greater blade area that could be integrated into existing aircraft without necessitating extensive modifications. Two prominent companies vied to resolve this critical issue: Curtiss-Wright, the original manufacturer of the narrow-bladed propeller, and Hamilton Standard, a leading producer of propellers for numerous military aircraft. Both companies recognized that the winning design would not only be manufactured in quantities exceeding 10,000 units but, more importantly, would directly influence the survival rates of thousands of American pilots. Throughout the winter of 1943, engineers at both firms toiled tirelessly, testing various blade shapes in wind tunnels, meticulously calculating stress loads, and constructing prototype hubs and pitch control mechanisms. American pilots continued to die in combat while these engineers refined blade chord lengths and twist angles. Hamilton Standard's engineering team pioneered a radical departure from conventional propeller design. Instead of slender, knife-like blades that merely sliced through the air, they proposed wide, paddle-shaped blades designed to grip the air like oars pushing through water. The blade chord would be dramatically increased, and the blade shape would be almost rectangular for much of its length before tapering near the tip. This design initially struck traditionally trained aerodynamicists as crude, but wind tunnel tests revealed astonishing results. The design generated significantly more thrust at low airspeeds while sacrificing only a minimal amount of top-end performance. Curtiss-Wright responded with its own wide blade design, featuring a more traditional elliptical blade shape but with a substantially increased overall area. The Curtiss design incorporated blade cuffs at the root, which smoothed airflow into the propeller hub and effectively reduced vibration. Both designs represented monumental improvements over the original narrow blades. In April 1943, Republic Aviation received prototype propellers from both manufacturers. Testing commenced immediately at Republic's facility and at Wright Field in Ohio. Republic's test pilots systematically evaluated both designs. The results indicated that both the Hamilton Standard and Curtiss propellers offered nearly identical performance enhancements, with climb rates improving dramatically with either design. Hamilton Standard provided slightly smoother operation due to its hydraulic pitch control system, while the Curtiss design integrated more seamlessly with existing aircraft systems and would be easier to retrofit to P-47s already in service or deployed overseas. Neither design was definitively superior in all aspects. The Army made a pragmatic decision, driven by manufacturing capacity. Both designs would be approved for production. Hamilton Standard propellers would be fitted to new P-47s built at Republic's Farmingdale facility, starting with the P-47D-22 model. Curtiss paddle blade propellers would be installed on P-47s manufactured at the Evansville, Indiana, factory and supplied as retrofit kits for earlier aircraft in England. This decision prioritized rapid deployment over lengthy evaluations to determine a theoretical best, and the dual sourcing would also complicate German intelligence efforts. Production commenced in June 1943, but manufacturing and testing delays meant that the first operationally equipped aircraft didn't reach England until late December 1943. Throughout December, P-47s were flown to RAF Wattisham, where mechanics painstakingly retrofitted them with the new propellers. The 56th Fighter Group, operating from Boxted in Essex, completed its transition by early January 1944. Group Commander Lieutenant Colonel Hubert Zemke immediately grasped the tactical implications. Dramatically improved climbing performance meant his pilots could now engage German fighters using vertical tactics that had previously been suicidal with narrow-bladed propellers. Zemke organized intensive training throughout January 1944, developing new combat procedures specifically tailored to the paddle blade Thunderbolt's enhanced climbing ability. He instructed pilots to engage German fighters in climbing spirals, maneuvers that would have previously left them dangerously vulnerable. He devised techniques where pursuing P-47s would pull up sharply if enemy fighters attempted to climb away, converting speed into altitude, and then dive back onto their targets with accumulated energy. With narrow blade props, these maneuvers would have left Thunderbolts wallowing at low speed. With paddle blades, they became lethal offensive tactics. January 4, 1944, marked a significant milestone. The entire 56th Fighter Group flew its first mission with all aircraft equipped with the paddle blade propellers. Pilots instantly noticed the difference. The aircraft climbed with an eagerness that seemed impossible for 7-ton fighters. Energy retention in vertical maneuvers improved dramatically, allowing Thunderbolts to follow German fighters into climbing escape maneuvers without losing position. The true test would come when they encountered the Luftwaffe over Germany. The combat debut occurred during escort missions in late January and early February 1944. American fighters encountered situations where German pilots executed their standard escape tactics, only to discover pursuing Thunderbolts matching their climbs. Initially, German pilots assumed they were facing a new American fighter type. When intelligence officers examined gun camera footage clearly showing standard P-47 Thunderbolts achieving this unprecedented performance, confusion rippled through Luftwaffe units. How could the same aircraft they had successfully evaded for months suddenly match their climbing performance? March 6, 1944, provided dramatic confirmation. Zemke led 48 Thunderbolts on a bomber escort mission to Brunswick, routing over Berlin. Luftwaffe controllers vectored more than 80 Messerschmitt 109s and Focke-Wulf 190s toward the incoming bombers. As the bombers approached at 24,000 feet, German fighters attacked using their customary tactics, diving through formations and then pulling into steep climbs to escape their escorts. Across the sprawling battle, Thunderbolt pilots matched German fighters in vertical combat for the very first time. Captain Robert Johnson, Lieutenant Walker Mahurin, and other 56th Fighter Group pilots caught German fighters in climbing engagements, destroying them at high altitudes. The group claimed 11 victories without losing a single Thunderbolt. More importantly, not a single bomber in their formation was shot down. German pilots landing after the Brunswick mission reported disturbing developments. American Thunderbolts were climbing with them. Multiple pilots insisted they must have encountered a new fighter type. When shown gun camera footage depicting standard P-47s achieving the described performance, their confusion only deepened. Luftwaffe technical intelligence urgently needed to understand what had changed. The first clue emerged from wreckage analysis in early February. A shot-down P-47D-23 was transported to the Luftwaffe test facility at Rechlin. Engineers examining the aircraft immediately noticed the propeller. Its blades were considerably wider than those on previously captured Thunderbolts. The technical intelligence report described the new design but initially failed to grasp its significance, concluding that the modification likely improved takeoff performance rather than combat capability. This misunderstanding cost the Luftwaffe valuable time. Throughout February 1944, more P-47 groups transitioned to paddle-blade propellers. The 4th Fighter Group received theirs in early February, and the 78th Fighter Group completed its transition by mid-February. By the end of the month, 6 of the 8 Thunderbolt groups in England were flying paddle-blade-equipped aircraft. Each group immediately reported improved combat effectiveness. German fighter losses steadily mounted as Luftwaffe pilots discovered that their standard escape tactics no longer worked. On February 21, 1944, Jägerschwader 26 lost 7 Focke-Wulf 190s in a single engagement with the 56th Fighter Group. Unit Commander Major Klaus Mayatusch filed an after-action report seething with frustration. His pilots had engaged according to established doctrine, disengaging through climbing attacks when pressed. Every pilot who attempted this maneuver was shot down. Mayatusch urgently requested clarification on whether the Americans had introduced a new fighter type and whether existing tactical doctrine remained valid. Luftwaffe intelligence had no satisfactory answer. German understanding improved through observation and wreckage analysis. By March 1944, Luftwaffe intelligence recognized that American engineers had modified the Thunderbolt's propeller to improve thrust at low air speeds, particularly during climbs. Reports circulated warning that American fighters could now contest vertical combat, recommending engagement only when holding a clear energy advantage and disengaging through level high-speed flight rather than climbing escapes. But changing tactical doctrine across hundreds of fighter squadrons proved impossible. Pilots who had survived by climbing away for the past year could not instantly reprogram their survival instincts. The scale of the transformation became undeniable during Big Week, the massive bombing campaign against German aircraft production facilities in late February 1944. From February 20 to 25, the 8th Air Force launched over 3,800 bomber sorties, escorted by more than 3,600 fighter sorties. The vast majority of American fighters were paddle blade-equipped P-47s. The Luftwaffe launched over 2,000 sorties in defense. Germans lost approximately 355 fighters destroyed, with another 100 damaged beyond repair. American fighter losses totaled 28 aircraft. The exchange ratio had shifted dramatically. Thunderbolt pilots discovered that paddle blade propellers created opportunities beyond simple climb performance. Increased thrust at low speeds improved acceleration out of dives, allowing Thunderbolts to build energy faster after high-speed attacks. Pilots could execute dive and climb attacks repeatedly, maintaining the initiative throughout extended engagements. Improved thrust also enhanced turn performance at slower speeds. While Thunderbolts still couldn't outturn Messerschmitt 109s or Focke-Wulf 190s in flat horizontal turns, they could maintain sufficient energy in climbing turns to prevent German fighters from gaining an angular advantage. Major Francis Gabreski, commanding the 61st Squadron within the 56th Fighter Group, became the leading proponent of what pilots called the climbing spiral. Gabreski would engage a German fighter at altitude, typically around 24,000 feet. Rather than attempting to outturn the enemy horizontally, he would maintain speed and pull into a climbing turn. German pilots, seeing the Thunderbolt climb, often followed, expecting the American fighter to lose energy and become vulnerable. But with paddle blade propellers, P-47s maintained their climb rate even while turning. Gabreski would spiral upward through 2 or 3 full circles, gradually reducing the German fighter's energy state until the enemy stalled or was forced to break off. At that moment, with the German fighter at low speed and high altitude, Gabreski would reverse, dive onto the target, and open fire from a position where the enemy had no escape route. Gabreski ultimately claimed 28 aerial victories flying P-47 Thunderbolts, making him the leading American ace in Europe flying a single aircraft type. Nearly all these victories came after his squadron transitioned to paddle blade propellers. In post-war interviews, Gabreski consistently credited the new propeller as the single most important factor in the P-47's transformation. The modification required minimal changes to pilot training. Aircraft simply did what pilots wanted, maintaining energy in situations where narrow blade-equipped Thunderbolts would have failed. The paddle blade program represented American industrial capability operating efficiently. From initial concept to widespread deployment required only 9 months. 2 companies designed, tested, and began manufacturing 2 different propeller designs. Republic Aviation modified production lines at 2 factories. The Army Air Forces developed new maintenance procedures, trained mechanics, and shipped thousands of propellers across the Atlantic. No single aspect was revolutionary. The achievement lay in the speed and scale of implementation. The United States identified a critical deficiency and corrected it faster than Germany could develop countermeasures. German aircraft designers possessed the technical knowledge to create similar improvements. Both Messerschmitt and Focke-Wulf employed experienced propeller engineers who understood the theoretical benefits of increased blade area. But the German war economy in 1944 could not support rapid modification programs. German aircraft production operated at maximum capacity, focused on producing existing designs in sufficient quantity to replace combat losses. Introducing new propeller designs would require retooling production lines, recertifying aircraft performance, updating maintenance manuals, and training mechanics. Production disruption would cost thousands of fighters when Germany desperately needed every aircraft. Germans were trapped by their strategic situation. They needed to match American improvements but could not afford the production disruption required. This highlighted fundamental differences in American and German approaches to aircraft development. American designers accepted good enough solutions implementable quickly. The paddle blade propeller was aerodynamically less efficient than more sophisticated designs. It created more drag than narrower blades at high speeds. It was heavier, requiring reinforced hubs and pitch control mechanisms. But it solved the immediate problem without requiring years of development to optimize every parameter. German designers often pursued theoretical perfection at the expense of practical implementation. German propeller designers worked on advanced variable pitch systems that would theoretically outperform crude American paddle blades. But these advanced designs existed primarily on paper, never reaching operational service in meaningful numbers. By March 1944, the paddle-blade Thunderbolt had become the standard American escort fighter in Europe. The aircraft was no longer a compromise platform, awaiting replacement by longer-ranged P-51 Mustangs. The Thunderbolt had evolved into a formidable air superiority fighter, dominating German opponents in most combat situations. The psychological impact was significant. American bomber crews, who had watched helplessly as German fighters climbed away throughout 1943, now saw enemy fighters chased down and destroyed in climbing combat. German pilots, already demoralized by increasing American numerical superiority, faced a tactical environment where their advantages had been neutralized. The Focke-Wulf 190, designed as superior to the Thunderbolt in nearly every performance category, found itself matched or exceeded in the one area where it had maintained clear superiority. The Messerschmitt 109 could no longer rely on vertical maneuvers to escape combat. German fighter losses climbed steadily through spring 1944. Many veteran pilots who had survived years of combat were shot down by Thunderbolts they thought they had successfully evaded. The full impact became evident during preparations for D-Day. Throughout May 1944, American fighters conducted intensive operations aimed at achieving air superiority over France. Thunderbolts ranged across northern France, attacking German airfields, destroying aircraft on the ground, and engaging any Luftwaffe fighters that attempted interference. Paddle-blade-equipped P-47s proved especially effective in these fighter sweeps. When German fighters scrambled to intercept, they typically climbed from lower altitudes to reach American fighters operating at 20,000 to 25,000 feet. Thunderbolts could now dive on these climbing German fighters, attack, then climb away before the Germans could retaliate. On June 6, 1944, as Allied forces stormed the Normandy beaches, Thunderbolts provided air cover throughout the day. German fighters that attempted to attack the invasion fleet or support German ground forces were consistently intercepted and destroyed by paddle-blade-equipped P-47s. The Luftwaffe managed fewer than 100 sorties over the invasion beaches during the critical first 24 hours. American fighters flew more than 8,700 sorties during the same period. This overwhelming superiority was possible because American fighters achieved kill ratios of 4-to-1 or better. The paddle-blade propeller, by eliminating the Thunderbolt's primary weakness, contributed directly to achieving the air superiority that made the invasion possible. Statistical evidence supported what pilots experienced. In the first quarter of 1944, before paddle-blade propellers became widespread, American fighters in Europe achieved an overall kill ratio of approximately 1.8-to-1 against German fighters. By the second quarter of 1944, with most American fighters equipped with paddle blades, the kill ratio improved to 3.2-to-1. By the third quarter, it reached 4.6-to-1. These improvements cannot be attributed solely to the propeller modification. American numerical superiority was increasing, pilot training was improving, and Germany was fielding inexperienced pilots to replace mounting losses. But combat reports make clear that improved climbing performance played significant roles in these victories. The Curtiss electric C-542S paddle blade propeller, the most widely used variant, featured 4 blades with a 13-foot diameter. Each blade had significantly increased area compared to its narrow-bladed predecessors. This substantial increase translated to dramatically improved thrust at low air speeds. The Hamilton Standard hydromatic paddle blade, fitted to later production P-47s, offered similar performance with operational advantages. The Hamilton Standard design used hydraulic pitch control that was simpler and more reliable than the Curtiss electric system. Total blade area was nearly identical, and combat performance was indistinguishable. The manufacturing effort required to equip the P-47 fleet demonstrated American industrial capacity operating at scale. Both Curtiss-Wright and Hamilton Standard produced thousands of propeller assemblies between June 1943 and December 1944. Each assembly consisted of 4 blades, a hub assembly, a pitch control mechanism, and mounting hardware. Blades were forged from aluminum alloy, machined to precise airfoil shapes, and heat-treated for maximum strength. Each blade required approximately 14 hours of machine time, not including raw material preparation and finishing operations. Distributing these propellers to operational units in England presented logistical challenges. Each propeller assembly weighed approximately 650 pounds and required careful handling to prevent damage during shipping. Propellers were packed in wooden crates with protective bracing and shipped across the Atlantic on cargo vessels. Voyages typically required 2 weeks. Upon arrival, propellers were transported to air depot facilities where mechanics installed them on aircraft. Installation required approximately 16 hours per aircraft, including removal of old propellers, installation of new ones, rigging pitch control systems, and conducting ground tests. Between January and June 1944, air depot mechanics in England retrofitted over 1,000 Thunderbolts while maintaining the operational readiness of frontline fighter groups. The tactical evolution of paddle blade Thunderbolt operations continued through the summer and fall of 1944. Pilots developed increasingly sophisticated techniques to exploit the improved climbing performance. One particularly effective tactic was the vertical scissors, where 2 Thunderbolts would engage a German fighter in a climbing dogfight. As the enemy aircraft climbed to escape one P-47, the second would position to attack as soon as the German fighter lost energy and could no longer climb effectively. The German pilot faced an impossible choice: continue climbing until stalling, making him an easy target for the trailing Thunderbolt, or roll out to maintain airspeed, allowing the lead Thunderbolt to execute a diving attack. Another significant development was the use of paddle blade Thunderbolts for low-altitude ground attack missions. Improved thrust at low speeds allowed heavily loaded P-47s to maintain speed and maneuverability even when carrying 2,500 pounds of bombs or rockets. Pilots attacking German ground targets could enter attack dives from lower altitudes, reducing exposure time to anti-aircraft fire. After delivering ordnance, paddle blade-equipped Thunderbolts could climb away from the target area more rapidly, again reducing vulnerability. Between April and September 1944, Thunderbolts flew more than 88,000 ground attack sorties while suffering approximately 820 losses to all causes, a loss rate of less than 1%. Paddle blade Thunderbolts allowed them to remain in frontline service even as longer-ranged P-51 Mustangs became available. Many fighter groups chose to retain Thunderbolts specifically because improved performance made them exceptionally effective in multiple roles. The 56th Fighter Group, commanded by Colonel Hubert Zemke and later Colonel David Schilling, flew Thunderbolts exclusively throughout the entire war, despite opportunities to transition to Mustangs. The group's pilots believed the rugged construction and 8-gun armament, combined with the excellent climbing performance provided by paddle blade propellers, made it superior to the Mustang for their operations. German fighter pilots who survived the war consistently mentioned the paddle blade Thunderbolt as one of the most capable American fighters they faced. Major Gunther Rall, who survived with 275 victories, noted in post-war interviews that improved Thunderbolts were far more dangerous than earlier versions. Rall stated German pilots had to treat paddle blade Thunderbolts with the same respect they accorded P-51 Mustangs, recognizing the American fighter could match German performance in most combat situations. Engineering lessons learned from the program influenced American aircraft development throughout the remainder of the war. Rapid development and deployment demonstrated that incremental improvements to existing aircraft could often provide better value than developing entirely new types. The P-47 itself benefited from continued improvements beyond propeller modification. Water methanol injection systems increased engine power to 2,535 horsepower for short periods. When combined with paddle blade propellers and their improved thrust characteristics, this further enhanced performance. The P-47M, introduced in late 1944, incorporated both and could climb rapidly, matching or exceeding the climbing performance of any German fighter. The financial investment required to develop and deploy paddle blade propellers was modest compared to the operational benefits achieved. Development costs for both Curtiss and Hamilton standard propellers, including wind tunnel testing, prototype construction, and flight testing, totaled approximately $3 million. By comparison, developing an entirely new fighter aircraft would have cost at least $100 million and required 2 to 3 years before reaching operational service. The paddle blade propeller represented exactly the kind of cost-effective improvement that made American air power difficult to match. Paddle blade propellers also highlighted the importance of feedback loops between combat operations and aircraft development. Problems with narrow blade propellers were identified by frontline pilots who filed after-action reports describing German fighters escaping through climbing maneuvers. These reports filtered through intelligence systems to reach engineers who could diagnose root causes and develop solutions. This feedback loop operated relatively quickly, with problems identified in combat leading to engineering solutions within months. German forces had similar feedback systems in theory but found them increasingly disrupted by the chaos of Germany's deteriorating strategic position. The strategic impact extended beyond direct air combat. The achievement of air superiority over Europe, to which improved Thunderbolts contributed significantly, allowed Allied ground forces to advance with minimal interference from German air power. During the breakout from Normandy in August 1944, American ground forces advanced under an umbrella of air superiority maintained largely by Thunderbolts. German ground forces attempting to retreat or reposition found themselves under constant attack from Allied fighters. Improved climbing performance meant German fighters that attempted to interfere with ground attack missions could be quickly intercepted and destroyed by escorting P-47s. The final major air combat involving large numbers of paddle blade Thunderbolts occurred during the Battle of the Bulge in December 1944 and January 1945. When German ground forces launched a surprise offensive through the Ardennes, bad weather initially prevented effective air operations. When the weather cleared on December 23, Allied air forces launched massive attacks against German ground forces and supply lines. Paddle blade-equipped Thunderbolts flew hundreds of sorties daily, attacking German armor, trucks, and artillery positions. Luftwaffe fighters attempted to interfere but were consistently driven off by escorting P-47s. By February 1945, organized Luftwaffe resistance over Western Europe had effectively ceased. German fighter units were being withdrawn to defend the homeland against increasing strategic bombing campaigns. Paddle blade Thunderbolts had played significant roles in achieving this air superiority, though their contribution was overshadowed by the more glamorous reputation of P-51 Mustangs. Military historians examining the air war have sometimes downplayed the Thunderbolt's importance, noting P-51s achieved more aerial victories and flew deeper into Germany. But this misses the critical point that the Thunderbolt's transformation through paddle blade propeller modification came at a crucial moment when German fighter forces still represented formidable threats. Between January and December 1944, Thunderbolts were credited with destroying 3,082 German aircraft in aerial combat, while losing 824 P-47s to all causes in the European theater. This represented an overall kill ratio of 3.7 to 1, comparable to or better than other American fighter types during the same period. More importantly, the Thunderbolt's transformation from mediocre climber to capable vertical fighter occurred during a period when such capability was most desperately needed. The post-war fate of paddle blade Thunderbolts reveals how quickly wartime innovations can be forgotten. As jet fighters entered service, propeller-driven P-47s quickly became obsolete. Most surviving Thunderbolts were scrapped or sold to foreign air forces. The technical achievements that made paddle blade Thunderbolts effective fighters were eclipsed by the revolutionary capabilities of jet propulsion. Few pilots who flew improved Thunderbolts in combat went on to positions where they could ensure the propeller modification received proper historical recognition. Yet, the paddle blade propeller represents a fundamentally important type of military innovation deserving greater recognition. It was not a revolutionary breakthrough that changed the fundamental nature of air combat. It was an evolutionary improvement that took an existing platform and eliminated its most critical weakness through relatively simple engineering. This type of innovation, less dramatic than revolutionary new technologies but often more immediately impactful, characterized much of American military success during World War II. The ability to identify problems, develop practical solutions, implement solutions rapidly, and deploy them at scale gave American forces decisive advantages. Engineering principles underlying paddle blade propellers remain relevant to modern military aviation, despite the transition to jet propulsion. The fundamental insight that blade area must be optimized for intended operating conditions, rather than theoretical maximum efficiency, applies to turbine blade design, helicopter rotor design, and unmanned aerial vehicle propulsion systems. Military engineers still face the challenge of balancing multiple performance requirements across different flight regimes. The German perspective on paddle blade Thunderbolts provides sobering lessons about the consequence of industrial and strategic weakness. German engineers understood propeller theory as well as their American counterparts. German aircraft factories were capable of producing improved propellers had they been given the resources and opportunity. But Germany's deteriorating strategic position, resource shortages, and increasingly disrupted industrial base made rapid improvement programs impossible. Paddle blade Thunderbolts succeeded not because American engineers were inherently more skilled, but because American industry could support rapid innovation while German industry could not. Wars are not won by single wonder weapons or brilliant strategies or revolutionary technologies. They are won by the cumulative weight of thousands of incremental improvements, each addressing specific problems, each implemented efficiently, each contributing to overall superiority. The paddle blade propeller was one such improvement among many, but it came at a critical moment when German forces were still capable of contesting Allied air superiority. By eliminating the Thunderbolt's primary weakness, the modification helped establish the air dominance that made the invasion of Europe possible and accelerated Germany's defeat. This achievement, born from the mundane work of propeller engineers, rather than the dramatic exploits of fighter pilots, deserves recognition as one of the decisive technological contributions to the Allied victory in Europe.